1 minute. I'm just setting up some codes so that we can see. Right. So yeah. Yes, I'm not talking yet. So very good afternoon to all the members, participating members. So how many are there right now? 327. Okay, I think we can start. Okay. Right. So let me take. Okay, let me use my hand note. That would be easier. Right. So what we have done so far, right? So I'll just summarize so that we'll have a connectivity. Fine. So yeah. Okay. So at the very earlier, maybe the quiz is there. So it will be helpful for the quiz as well. Not audible? Not audible, not audible, not audible. Hello? Audible. Okay. Yeah, somebody who is having issues, figure it out. Right. So we started with there is something called quantum parallelism. Okay. Right. That is a very initial stage. Quantum parallelism. Okay. So quantum parallelism. We started with that. What is so parallelism is for a given value of various x, we can find f of x. Okay, right? Okay, so we can find all f of x for all x values simultaneously, not in, let's say, a minimum number of steps. It is not, it is just in one step. That is in a single step. That is a very important, right?
Ashwath sir.
Yes, sir. Some screen is not visible.
Yeah.
Screen is not. Please share the screens. Yes.
Thank you for saying. Right. Yeah, I think now.
Yes, sir, it is visible.
Single step. Okay. So what I was saying, where did we start? We started with quantum parallelism. Actually, all those things have a connection to whatever we are going to discuss today. That's why I'm just trying to recollect what is required for us for today. So 220725. Okay. So quantum parallelism allows me to find multiple values of a given function simultaneously, that too in a single step. That is the first thing. Next thing is Dutch algorithm. Okay. So what it does, Dutch algorithm does is, it takes the quantum parallelism Okay. To that, it adds uh, quantum interference. Okay, and gets us not only multiple values of argument, also some combinations of functional values. What combinations? It can be sum of all the function values. Okay, right? So the addition modulo sum of all argument a function, or I can say sum of all the function values, functional values for all the argument in the sense x values, argument values. Okay, this is Dutch algorithm for you. Okay, so we started finding function x1, x2 and up to f of xn. Okay, not only that, we will go on to sum them and find them. The next thing is Dutch. Okay, Dutch Joyce algorithm. Dutch Joyce algorithm. Okay, yesterday we discussed this one. What is this one does is, let's say somebody has used a function f of x. Remember, any function in binary system, or let's say in our quantum system, it takes inputs 0, 1 in this format and gives out 0, 1. Okay, right? So this is a string of zeros and ones representing the input. Okay, input information. Okay, which can be processed by unitary function. Okay, f of x, and gives us the output. Okay, the example task would be finding number 7 from 0 to 9 set. Okay, so every time when you query, you get 0 means you are not succeeded. If you get 1 means you succeeded. Okay, that is a Dutch Joyce algorithm preamble. Okay, so what Dutch Joyce algorithm does is, okay, here itself using that information. Okay, and somehow it is a, okay, 1 minute, right? Somehow it is converts that into a game, a kind of a game between two people. That is, A is there, B is there. B is asked to use a function which is a constant function or a balanced function. Okay, now A should make a query to B. B sends the response to A. So one complete circle is one iteration. The question is, how many iterations are required? How many iterations are required to find the nature of nature of f of x. Okay. Classically, as we can see, if the input size is n, input size is n, then n by 2 plus 1 is a maximum number of attempts required. Okay, but using a quantum superposition and quantum interference, okay, and quantum parallelism, so many things are there. Superposition, interference, parallelism, using you are actually coming with a quantum circuit. Using them, one could find the nature of f of x in a single step. Okay, single step, not even minimum or something. So that is a Dutcher's algorithm for you. Okay, let's export this to be on safe side. Okay, now that is the summation. In doing those things, we understood, we used few tricks, the gate tricks. What the gate tricks we understood is, okay, let me write down. If you just take Hadamard acting on 0, as we know, it gives you this one, a equal superposition, like without any relative base phase between 0 and 1. Okay, which, and what about this one? This creates a relative phase. Okay, and what we can do, put them into one simple equation like this. H acting on x is equal to, okay, summation over x belongs to 0 comma 1, okay, right, minus 1 to the power of z or x into z. Let's say, instead of saying x into z, get z. Okay, so now you see, whenever x takes 0, I'll get the first one. Whenever x takes 1, I'll get the second one. For, okay, just this is a correction here. This is z belongs to 0 comma 1. Okay, and this entire thing I can generalize if see here x belongs to 0 comma 1. In that case, I am getting this kind of output. If x belongs to 0 0 0 1 1 0 1 1, which is actually 0 comma 1 tensor square. If that is the case, okay, you can generalize this same expression. If somebody has any issues, sir, please once explain the Dutch algorithm in IBM by doing practical. Yeah, I will show that today. Okay, right? Dutch algorithm I'll show you. Fine. Okay. Yeah. Right. So I can generalize this expression as h acting on x, where x could be x belongs to 0 comma 1 tensor square, okay, is equal to summation over, now z also becomes 0 comma 1 tensor square minus 1 to the power of x dot z, z cat. Okay, remember we forgot to put a square root of 2 here. That should not be done. You have to remember every time, divided by 2 to the power of 2. So this is what one has to do. Okay, right? Let me put this phone to, yeah, fine. Now for any x, means x belongs to 0 comma 1 tensor n. In that case also, h acting on x becomes z belongs to 0 comma 1 tensor n minus 1 to the power of x dot z, z get 2 to the power of n. Okay, we should remember that. Fine. Now I was saying so far x dot z. Okay, what is this x dot z is? If x is just one number, z is just one number, x dot z is simply 0 into 1, it is 0. Okay, if x is 0 comma 0, z is 0 comma 1, it's a bit string I'm talking about. X dot z there is 0 into 0 plus 0 into 1. What I'm taking, the first entry I'm multiplying to first entry, second entry I'm multiplying to second entry, and then adding them, which is going to give me 0 anyway. Okay, but not every time. There are cases. Okay, if x is 1 1, z is 0 1, x dot z is equal to 1 into 0 plus 1 into 1, it is 1. You see, we are getting something else. Okay, so this is like a, a, a vector dot product. If R is some xi plus yj, R1, R2, x1, y1, x2, y2, okay? In that case, R1, R2 dot product is x1 into x2 plus y1 into y2. That is a dot product. Okay? Similarly, that is what we are following here. Same analogy. This is very much required for us in today's session. Okay, right? Now, let's get to the Bernstein-Swajrani algorithm. Okay, right? 1 minute. Let me set up a few things. Yeah. Okay. Yeah. Yes. Just a minute. Give me a second. Yes. So Bernstein-Swajrani algorithm, before going there, okay, let's understand some motivation to go there. Okay. For example, as we know, the information storage, okay, information storage classically, how it is done on a hard disk or anywhere. Let's say if you just take a magnetic strip, if there is a division, small parts, I'm talking about classical memory, okay, where all the dipoles were arranged left, I'm treating as 0, all are arranged as 1, I'm treating as 1, left is again 0, right is 1. So this is how we store the information, right? Okay, the bits, right? But there are some errors. Errors would lead, instead of 0 1 0 1, errors would lead to 0 1 1 1. Okay, what happened is the third bit got flipped. This is got flipped. maybe due to some internal error or some problem. Okay, now if you just take a bit string, let's say if you just take a bit string x, take any bit string, x is as a bit string. Okay, I'm not saying what is the length. Let's say 0 1 0 1 0 so on, let's say n length bit string. Okay, now let's say you are processing through a quantum as a system. Internally, let's say system has got some problem. Okay, it flips some of the bit strings. Okay, how it flips is, let's say there is a string which is like 0 0 1 0, like that. Let's say some 0. Let's say this is a bit string. Right now, if you call this as a x, so this is a bit string. Like let me call this internal bit string. Okay, internal. Wait a minute, what is going on? Internal bit string. Okay, what it mean by this is, let's say the third bit is flipping inside the system without having any our intervention. It is a system problem, maybe some malfunction in the a particular gate inside. So that would lead to something a wrong conclusion. So how it is going to do is, it is going to add up something to the actual x string and leads to a wrong. So s would lead to x prime by one of the bit string is being flipped. Okay, so that is a motivation, right? So I want to know what is this internal bit string, or you may call it as something called hidden bit string process, or bit string process, or procedure, something like that. I want to know, if I, let's say I don't know, for example, if I don't know, at least what is the result it is causing, from the result can I nullify or mitigate that? So that is a question. Okay, the question is to find the internal problem, internal bit string flips. Okay, or from the result can we mitigate such bit strings? Okay, I want to nullify that so that I don't see such effects. Okay, for that what we can do is, okay, so there is some technique, classical techniques itself you can follow, right? So what is that classical technique is? Okay, right, let's see the classical technique. Okay, for example, let me take a very simple example. Okay, right, now the bit string which is causing the problem is, let's say s equal to 1101, which means it might flip first one, second one, and the fourth one, right? So this is going to flip if the x is something like 1011, this one is going to flip the first one, second one, third, fourth one. The bit, this is a internal hidden flip mechanism or errors. or errors. Okay, flip errors. Now I want to find this. Okay, how can I find is very simple. There is simple technique which we can follow. Okay, let's say you just take first find the length of the bit string we are feeding. Bit string we are feeding to the system. Okay, okay, the length is 4 na, right? So what do you do? So n is 4, choose 1 0 0 0, right? If you choose one input as 1 0 0 0, you take a dot product of that with s. S is 1 0 1. Okay, now if you use a dot product, let's say you call it as a sum. So this is your any signal, example signal na. So the example signal get affected by such as. So instead of sending example my actual signal, I'll send some x test, which is like this. Okay, now you try to find out what is the sum, like sum of all the individual products, like a dot product, like 1 multiplied to 1. Let me do that. 1 multiplied to 1 plus 0 multiplied to 1 plus 0 multiplied to 0 plus 0 multiplied to 1. Okay, this is 0 0 0 and only 1. You got 1. Now this time you take another test, which is you just push this 1 to the second digit. Okay, take the, let's say this is yes, we know, roughly yes, we know. Okay, we are taking yes, and to the yes we are multiplying x test. Now you just do that again. 0 to 1 plus 1 to 1 plus 0 to 0 plus 0 to 1. Again, the last two is 0, first one is 0. I'm getting 1 here. Okay, and do one more test. What is that is, this time we move the bit, non-zero bit to third one. Take 1 1 0 1. Okay, again 0 comma 1 plus 0 comma 1 plus 1 comma 1 into 0 plus 0 into 1. You see all are zeros. 0 0 0 0, right? Okay, now do one more test. Okay, now this time 0 0 1 into 1 1 0 1. Try this now. 0 into 1 plus 0 into 1 plus 0 into 0 plus 1 into 1. It gives me 1 because 0 0 0 and 1. Now if you carefully see what you got, the result, right? So let me write down the result. Result is x test 1, okay, plus x test, sorry, no, not plus, x test into s, comma, x test 2, comma s, x test 3, comma s, x test 4, comma s. If you just see this, in fact, what you got is 1 1 0 1. Okay, so what it is conveying for me is, when I take a string of tests, x test, which belongs to 1 0 0 0 1 0 0 0 0 1 0 0, 0, 1. If I take the tests multiply with the S, I will get a result which is having the information of nature of S. It is obvious. I'm multiplying with the S, so I'll get the essence of S in the result. Okay. Okay, so people thought that can we use this technique or this logic to get to know if there is a system error which creates such bit string S, bit flip mechanism internally. Okay, I can't exactly know what is the nature of like where the problem is there in the system, but I know from the result I can address where the problems are. Okay, so this is the main objective of this Bernstein's Vajrani algorithm is finding errors in the circuit or errors in the computation. Okay, right? So for that, what people have come up with the technique is they defined. Now we'll talk about Bernstein Vajrani algorithm. Okay, right? I think I have a PPT which is made for you people. Okay, right. Yeah. Okay, let me go to second slide. If you see, the Bernstein-Vajrani algorithm, in fact, started developing in 1992, okay, by Ethan Bernstein and Umesh Vajrani. And they introduced to the community in 1997. So they took some time. If you see the trend of the quantum computing research growth, 90s is the main growth actually. Shor's algorithm came in 92, 96 is Grover's algorithm, and 97 roughly during exactly this time, Bernstein's Vajrani algorithm came. In fact, this algorithm would reveal how quantum computing can be more effective and faster compared to classical algorithms. Okay, right? So, yeah, there is a statement here. It says it is an extension of Dutch-Joyce algorithm. We'll come to that, how it is. Okay, so Bernstein's Vajrani algorithm is an extension of Dutch-Joyce. What is Dutch-Joyce algorithm? F of x being constant or balanced. Okay, so standing on the same kind of a nature, let me devise a function which is equal to x into s modulo 2. Okay, I'm defining a function which multiplies given input bit string argument to the s hidden bit flip string. Okay, right, and multiplies and sums. If the sum is 0, it gives 0. If sum is 1, it gives 1. Let's say if sum is more than 1, let's see, more than 2 sometime, let's say x is 1 1 1. Okay, x is 1 1. Oh, sorry, s is again 1 1 1. Now x dot s, you see, 1 into 1 plus 1 into 1 plus 1 into 1 plus 1 into 1. This is actually 4. Okay, so you can't say anything more than 0 and 1 in binary system or anywhere in quantum computing. So this has to be seen in the modulo 2. What is this value in modulo 2? 0. Okay, right? So that is what I mean. So they defined a function like this. Okay. And now this is the function which captures or represents the problem in the system or the circuit. Means there is some internal X going in input that should process properly, but if there is a problem somewhere which is represented by X, that X changes to some X prime. Okay, what is that change going from X to X prime is some flip is happening, okay, with a S. Okay, it is like I addressed earlier. So okay, right now this is the definition of Bunsen-Vajrani algorithm. So in this way, function we were targeting to find the function. Okay, the kind of a function, what kind of a function is that? Or by knowing the result, we could find the function. Okay, right, let me take a little bit thinner, hopefully. Okay, fine. I just deleted, I guess. Okay, now f of x is equal to x dot z modulo 2. This is a mathematical function. Okay, a mathematical function for Bunsen-Vajrani algorithm. Okay, right? So this is very, very important. Now, what we will do is, okay, classically I can do in that way, right? Quantum mechanically you can do in a different way. So the classical way was showing here, right? Okay, so a function is yeah, right? So quantum mechanically how it is done is, okay, so I want to know the nature of the function. Okay, what people do is, let's say some x is going through a quantum gate. Okay, right, I'll take an unitary function which is making some change to x. Okay, and I'll take a ancilla qubit, right, an ancilla, right? Okay, so like usual way of doing things is, okay, what usual we do is, depending on what is this u of f, we take that, we do a C naught gate. Okay, depending on u, I want to edit the ancilla and read the ancilla. Okay, and find out what is u of f. Very simple. Or you can say r f of x. This is a usual trend. So I want to know what is the effect happening here. I'll just send something through it. Okay, if it causes some effect on the x, what kind of effect I take from that information, feed it to ancilla through some C0 gate. Okay, and find the information. Okay, right? So there is one more technique you can do is, okay, take unitary functions. Let's say it is taking some inputs. Let's say 4-bit qubit information is going in. You feed Hadamard gates, Hadamard here Hadamard here. Okay, 4 Hadamards. Now, the moment you do this, there is something called phase kickback occurs. Okay, right? So, which leads to phase kickback. I don't know whether you know it, but we'll discuss phase kickback, right? So the phase kickback means instead of information flowing from top to bottom, information flows to bottom to top. Reverse, that is a phase kickback. Okay, so let me, yeah, right. We will try to first understand what is phase kickback, and then we will get to understand how this Bernstein-Swajrani algorithm is going to help me to find the internal bet flip string yes. Okay, right? So yeah, wait a minute. I'll just take the circuit for phase kickback properly. So maybe I'll explain. Okay, phase kickback I can explain using a simple, yeah, simple maybe, yes, a simple circuit. Okay, right? Usually, what we usually think is if I just take a CNOT, conventional information flow, conventional information flow, information flow. Okay, right? If this is 0, if this is 0, I'll get output 0 0, right? If I have 1 here, I have 0 here, I'll get 1 there, I'll get 1 here. Okay, what is happening here is the I, like first qubit being in 1, the information of first being in 1 is flowing down. Okay, right? Suppose if I take like this, like 1 and 0, what output I'll get is I'll get just this one only. I'll get this output only, right? Because control is low, the target is not going to flip. Okay, so the information always flows down. Information always flows down. In the case of C0, let's say control not gates or controlled unitary gates, any controlled unitary gates. Now, if I say, right, if I say there is a chance information can go upwards. What I mean is, even though I choose the control not gate like this, whatever is the target is going to influence the from target to control information flows in a reverse fashion. Flow in reverse direction, which is what phase kickback is. Okay, right? So to do that, what one has to do is, instead of just leaving C0 gate as it is, okay, so one has to do start with the Hadamard gate and a Hadamard gate here. Okay, right? And see, just to see whether information flowing down to up to bottom, I need to have the top and bottom two things should be different. Okay, right? You see here, when I took both are same, I am not seeing whether information is flowed up or down. Okay, when I choose 1 0, I see information is flowing from top to bottom. When I take 0 and 1, even in this case, information flowing from top to bottom, but the input and output remains the same. So I am not able to recognize that the information is flowed or not, but in fact information is flowed. Okay, so one catch is here. I want to see whether information is flowing down or up. I need to have the inputs must be a different. So let me choose, this is 0 ket, this is a 1 ket. Okay, right? Fine, 0 ket, 1 ket. Now at this point, okay, at this point you just try to see what is the, let's say, let me call psi 0, psi 1, right? So psi 0 is 0 ket, tensor 0 ket, sorry, 1 ket. Okay, now psi 1 is Hadamard acting on 0, tensor Hadamard acting on 1, which I will easily write down as tensor, sorry, superposition of 0 with the 1 positive, superposition of 0 with -1 relative phase. Okay, so this is what I have here. Now I can write this as a plus ket state minus ket state. Okay, right? So plus ket state minus ket state. Now you act as C0 gate from top to bottom. Okay, right? So what I have here is I have a plus gate, I have a minus gate here. Carefully, you see, I'm not doing anything, I'm just writing as this. Now, what is the effect of C0? I should know. So let me explicitly write what is my psi 1. Psi 1 is 0, 0. I'm just multiplying this plus 1, 0 plus 0, 0, 0, 1. I'm sorry. Let me write down neatly according to the order. 0, 1, 1, 0 minus 1, 1 divided by 2 or square root of 2 square. That is what I have. Okay. Now C naught acting on psi 1. Okay. So left entry is control, right entry is target, as we know. So first one is not going to change. Second one is also not going to change because control is 0. But third one is going to change. Fourth one is also going to change because controls are 1 in third and fourth. Okay, denominator as it is. If you carefully see here, what is happening here is the probability amplitudes of 1, 0 and 0, 1 are actually interchanging. That is what happening here. Okay, that is very, very interesting. So what you can do, right? You can just see whether what is this psi 2 would look like. Psi 2 would look like, no? Okay. Now let me just to do some, if I am able to take some common, let's take some commonality here. Okay, right? So there is a 0 common, 0 common. Let me take a 0 common. 0 plus 1, 1 common, 1 minus 0. Okay, right? So I don't want minus lingering inside, I want to bring it outside. Okay, so right, let me do that. 0, 0 plus 1 minus 1, 0 ket minus 1 ket divided by 2 square root. Now, okay, what is this, by the way? This is plus ket minus What is this, by the way? Minus ket with respect to denominators going in them. Okay, there is 1 square root of 2 goes here, 1 square root of 2 goes here, and I'll get this. If you carefully see, right here, the second qubits are in the what? They're in superposition states, right? They're in superposition state. Now, what is happening here is, okay, yeah. Now let me do Hadamard action on right sides. Okay, so I have psi 3. I want to find psi 4. Okay, right? So psi 4 is Hadamard acting on two Hadamards acting on psi 3. I have psi 3, sorry, psi 2. How I am naming after C0? After C0, it is psi 3. Okay, I missed psi 1, psi 2, and this is psi 3. Okay. Okay, this is psi 3. Psi 2. Okay, this is psi 2 for me. Now, which is equal to Hadamard acting, you just take this entire thing. Hadamard acting on 0 tensor, Hadamard acting on plus, minus Hadamard acting on 1, Hadamard acting on minus 1. Okay, right? So as you guys know, Hadamard acting on 0 gives me what? Plus ket. Hadamard acting on 1, sorry, plus gives me 0 ket, minus Hadamard, sorry, Hadamard acting on 1 gives me minus ket. Okay, minus ket. Hadamard acting on minus ket, I'll get a 1. Okay, so now if you carefully substitute explicitly what these are, you would get very, very interesting things like 0 ket plus 1 ket divided by square root of 2, 0. 0 minus 1 divided by square root of 2, 1 ket. Okay, let me explicitly write down 0, 0 plus 1, 1, 0 minus 0, 1 plus 1, 1 divided by 2 square root. This is a psi 3 for you. Okay, so what we started with, okay, what we started with is a 0, 0, right? And 2 Hadamards, a C0 followed, and 2 more Hadamards I use. If you carefully see, the probability amplitudes were shifted like anything. Okay, so in fact, what is this, by the way? What is this? This is actually, okay, yeah, 1 minute. This is Hadamard square acting on, right? Hadamard square acting on, okay. Or you can also see that this is in fact a result. This result would come if I have C0 like this. Okay, right? So what was my inputs? My inputs are 0 and 1, na? 0 and 1 input, 0 and 1, 0 and 1. So it will give me 1, 1. Okay, right? But what did I start with? I start with this one, which is 0, 1. Okay, right? So the information flow is always top to bottom. So it should give me that. Okay, but here the information flows down. Because of that only I did not see any effect on 1. But if the information flows from bottom to top, okay, my result gets changed from 0 to 1 here. How this is happening going from here to here is very simple. You enclose this one with Hadamard gates, C0 gate, it just becomes a flip. Okay, they become equivalent. That is a phase kickback. So that is what we had in the Bernstein-Swajrani algorithm, right? So I showed here the C0 gate from bottom to top was there. When I enclose within Hadamard gates in a reverse C0, they become equal. So basically what I'm saying is, I want to, if the information is flowing like this, I want to information flowing this. If I want to send it opposite way, what I do, I just take the same thing, enclose with the Hadamard gates throughout. That's all. That is going to ensure that. How? If I have something like this, if I send plus minus, I usually get plus plus. I hope I'm right. Okay. But if I send plus here, minus here, information flows like this. Okay. Right. So this is a phase kickback for you. What we'll do, we'll take quick break for 5 minutes. Okay. And then use this phase kickback and the understanding of, okay, the understanding of querying the registers many times to find the S using this function, and we'll see in one single attempt we are going to find what is the errors in the system using this technique. It is called Bernstein-Swajrani algorithm. Okay, I'll show you a simple workflow to understand, then you would get it. Okay. Okay, then let's take a break of 5 minutes. Last diagram somebody was asking.